Representative Turkelman. You see me in such fine quality, epic AP environmental science educational videos such as apes does not mean simians and productivity? What are you talking about? Okay, for this particular video, ladies and gentlemen, we are looking at gross primary productivity, net primary productivity, and respiration. Now we're going to be doing some problems, a few problems here on the sheets, and hopefully that will help you guys out. Now there's a few definitions we need to cover. Gross primary production, otherwise known as GPP, that's the total amount of CO2 that is fixed by the plant in photosynthesis. Now remember the idea about plants that they look at photosynthesis, you know, with carbon dioxide coming in, plant gives off oxygen, and ultimately it creates biomass. Biomass not only in plants, but you got to think about the animals too. So when you look at biomass, you're looking at how much does all living things weigh. That's the biomass. But we can't have that unless we have a gross primary production. Now in this case here, we're looking at the plants in photosynthesis. Respiration is the amount of CO2 that is lost from an organism or system from metabolic activity. Okay, that's the other thing. And then net primary production. That's the net amount of primary production after the costs of plant respiration are included. So when we look at gross and net, let's take a look at it. If you were working at a job and you got $10 an hour, you worked a 40-hour week, you'd get a gross pay of $400. Now, in real life, you would have taxes. So let's say the taxes take $100. So gross pay of $400. Take away the taxes, the cost, if you will, of $100. Your net pay is $300. That's what you get to take home. So when we look at living things and when we look at ecosystems, really ultimately we're looking at our net primary production. That is how we make a determination about ecosystems as to how productive they are. Now, we are going to have some problems. We can do a little bit of couple of problems here. So this is what I want to do with you guys here. For that, hang on one moment. And I get my paper because I got a few notes in here. Okay, so what we did here, they did an experiment where they took a bottle, put it in water, and they got some organisms in there, and they did that for 3 bottles. The initial concentration of oxygen was 8 milligrams of O2 per liter. That's called dissolved oxygen, okay? Now, what they did with the bottle, this is your initial. So this is already looking at production and respiration, the whole bit. We take that bottle, we put that and expose that to the light for a certain period of time. Now, why would we expose that to the light? To do the photosynthesis, so that photosynthetic organisms can actually go and crank out O2, and that's how we're measuring it. So when we look at the initial bottle of 8 and the light bottle of 10, that tells us photosynthesis has happened and we got a little bit of extra O2 in there. Now, what about the dark bottle? Well, with the dark bottle, we start out with the same concentration of O2 as our initial. We cover up the bottle so that no sunlight penetrates it. Now, if you don't have sunlight penetrating it, guess what? No photosynthesis is going to happen. Now, the photosynthetic organisms inside of that bottle are not going to sit there and go to sleep or do nothing. They're going to start feeling kind of hungry, and they're going to start consuming the energy that they have stored up when they were doing the photosynthesis. But since there's no light, they're doing the consumption. So what's happening is they're now sucking in the O2 and releasing the CO2 out into the air. That's how it works. Okay, so our dark bottle has 5 milligrams of O2 per liter compared to the initial of 8. So how do we compare, how do we go and calculate our NPP, respiration, and GPP for this? Okay, so when we look at it, we have to take into account our light bottle and our initial. So this is going to be important for us for our light and our initial, and our dark and initial. because really we need to compare what did we start with and what happens when that same stuff is exposed to the light. So this is where we take the light, in this case R10, minus the initial. The initial was 8. Okay, so what's happening here? We can look at the light as our gross primary productivity, right? That's what we had. The initial, we're considering that to be the respiration, okay? We're looking at that as the respiration, and what that's going to give us is our net primary productivity. And it's going to be fairly low, so 10 minus 8 is 2. That's our net primary productivity for this problem. Now, we got the NPP, check. All right, now we got to figure out our respiration. Now in the respiration, we do have our dark bottle, but we have to compare it to our initial. Okay, now in this case here, our initial is an 8. Okay, so here's our 8, that is our initial. Okay, and we're going to subtract the dark bottle. Okay, and that's going to be 8 minus 5, and that's going to give us our respiration. Okay, so that equals 3, which is our respiration. Okay, now we have 2 of the 3 pieces that we need. We figured out what our net primary productivity is for this bottle, for the bottles. We looked at our respiration. Now we can look at the gross primary productivity. They show you an equation here. I'm not even going to worry about that because now we know our basic formula. We can take the gross primary productivity is equal to the net primary productivity plus the respiration. Okay? Doesn't matter how big or little that the numbers are. So in this case, our net primary productivity was 2 from this problem because we figured that out. So there's our 2 plus the respiration of 3. And you'd say, but wait a minute, wouldn't the 3 be a negative? Well, no, remember, that's part of the cost that the photosynthetic organisms, when they were doing the breathing, okay, they were doing the respiration. So now we can look at NPP plus R, so our net primary productivity, plus our respiration, and that's going to add them together, and we walk away with the 5, which is equal to their gross primary productivity. That's how it works. I don't think they're going to get that complicated, but I wanted to go and mention that to you guys. Okay, I'm going to go ahead and I'm going to erase this. And let's take a look at the next page here. Whoops. There we go. Let's take a look at our next page. So for these, they're a little bit different because we're not dealing with bottles. Okay? We're now, they're giving us the values of GPP, NPP, whatever. So let's take a look here. So we have if the gross primary productivity, or GPP, for a patch of forest is 10 kilograms times calories per square meter per year, and the amount of carbon dioxide leaving the ecosystem. Oh, don't ask how we measured this, is 5 kilograms times calories divided by meters squared times year. What is our net primary productivity? Okay, so for this one, let's take a look. There's 2 numbers that they've given us. Okay, they've given us a 10. Now that's our GPP, right? That equals 10. Okay, and then they gave us, they said, and the amount of carbon dioxide leaving the ecosystem. Wait, what's happening there? Well, remember, we're not talking just plants, we're also looking at other living things because it's a patch of forest, so it's not just plants. Okay, this might be a little bit confusing, but since we're not dealing with just plants here, folks, we're also dealing with all the animals and all that. So what happens when they say carbon dioxide is leaving the ecosystem? Okay, that means it's being sucked in. Okay, if it's being sucked in, that's the respiration for us. So that means our respiration is going to equal 5. Okay, and they're asking us what's the NPP. Okay, so the NPP is equal, we don't know what that is. Okay, so with that, all right, NPP plus R is equal to GPP. That's our basic formula that we have. Okay, so this is X plus 5 equals 10. And some of you guys are saying, is the math that simple? Yeah, actually it is. So in this case, our NPP is equal to 5 kilograms, okay, times calories over meters squared times year. And that is the actual answer for this problem here, for problem number 1. Now remember, on the exam you have to show all the work and your units, okay? You've got to keep going with your units. All right, I'm going to have to erase this one. And let's take a look at number 2. Now number 2 is a little bit different because we're not dealing so much with gross primary productivity, respiration and whatnot. We're looking at energy. Now remember we talked about the pyramids, okay? And sorry guys, I got to take a quick look at my timing here. All right, we should be able to do this. Okay, so in the patch of forest in problem 1, that's this one, how much energy is available to the primary producer level for herbivore consumption? Okay, assume 1 kilogram of carbon produces 10,000 kilojoules. Well, we need the net primary productivity to work with, okay? Now, why in the world do we need the net primary productivity to work with? Why don't we work with the gross primary productivity? Well, remember, the net primary productivity is what the forest has produced overall, or whatever this is. Yeah, the forest. That's what has been overall produced in there. So we have our net primary productivity to do that. Okay, and we calculated that to be 5 kilograms calories per meter squared times year. That was our net primary productivity. Now, that means, so that's 5 kilograms, okay, that's what we have. Now notice they didn't ask about the area, what was the size of the forest, that doesn't matter. What does matter is we need that NPP, we need to know what's the net that we're getting out of it. Now it says, assume 1 kilogram of carbon produces 10,000 kilojoules. Okay, so I'm thinking here, look, if I'm getting 5 kilograms, okay, I'm going to multiply this. I'm going to multiply this by 10,000 kilojoules, okay, over, for every 1 kilogram times calorie over meter squared times year. Now notice you've got to make sure that your units cancel out. You'd say, well, why do we need to put this on the bottom? Well, the idea is we want to figure out how many kilojoules is this thing producing, okay? So in this case here, we want to make sure our units cancel out. I know this kind of looks weird, but remember, you want to cancel out your units so that you're left with kilojoules, right? So 5 times 10,000 gets us 50,000 kilojoules total. Okay? That's the amount of energy that is total that's in the plants, the producers, the grass, the trees, and all that. Now remember though, you're looking at how much energy is available for herbivore consumption. Okay? That's the question. Well, remember, if you guys remember in lecture, we talked about that idea, about that only 10% of the energy goes from one level to the next level up, and then 10% of that energy. So when we look at 50,000, okay, really only 10%. Now you should know about converting percents and all that. So 50,000 times 0.1 gives us 5,000 kilojoules. So that's really how much energy that the primary consumers are going to get, our herbivores. Okay, that's how much energy they're getting. What is out there overall is 50,000. Okay, but ultimately what they're getting is only 5,000 kilojoules of this energy. Okay? All right. Any questions, guys? Okay. Let's take a look at number 4 here very briefly, okay? Imagine we run an experiment on this algae. Cool. We place equal amounts of algae to a light bottle and a dark covered bottle. Measure dissolved oxygen in both bottles, find it's 10. Let both bottles sit for a week. In a week, the light bottle has a dissolved value of 11. Okay, so our initial is 10. Okay, that's our initial. In the light, okay, we have 11. And in the dark, we have 5. Okay, so now you have the conditions here. Go back and look at that first problem that we worked through together, okay? That should help you guys out. Okay, I'm hoping that this will benefit you guys, all right? And in the meantime, this is Biff Turkelman signing off.